Hello and welcome to the Deep Dive. Today we're embarking on a truly fascinating journey, really exploring the very fabric of our existence. You look around and you see so many different things, don't you? Trees, buildings, that hot cup of chai in your hand, perhaps. But what is it really all made of, at its core?
Absolutely. And our mission today really is to unpack the fundamental building blocks of everything you encounter, from the air you breathe to the food you eat, and importantly, how these essential components behave. It's truly a shortcut, I'd say, to understanding the physical world around us, and a chance to truly grasp some of those everyday mysteries.
Fantastic. And for you, our listener, you might be wondering why the aroma of your hot food seems to travel faster than cold food, maybe, or how a spongy dosa can be squeezed so easily while, a rock is so incredibly rigid. We promise by the end of this deep dive, you'll have some truly aha moments about these everyday wonders, really connecting the dots between the invisible and the observable. Okay, let's unpack this. I. What exactly I matter, the basics of our universe? So, to begin our deep dive, let's start with the absolute basics. When scientists talk about matter, what exactly are they referring to? What does something need to be to be considered matter?
That's an excellent starting point, really, because it frames our entire discussion. In the simplest, most fundamental terms, matter is anything in this universe that is made up of material, which fundamentally occupies space and has mass. It's the stuff, you see, everything is composed of.
The stuff everything is composed of. Okay, that sounds incredibly broad. So, when you say everything, can you give us some truly diverse examples from our surroundings? Things that fit this core definition? Maybe things we might not immediately think of as matter, but actually are?
Certainly. And when I say everything, I truly mean it. Think about the incredible diversity of the air we breathe, for instance.
Right, air. Feels like nothing.
Exactly. Feels like nothing, but it definitely takes up space. Then there's the food we eat, the solid, immovable stones you see outside, fluffy clouds floating high above, distant, massive stars, all living plants and animals, even a tiny drop of water or a single minute particle of sand. Every single one of these you see is matter.
Wow, it's quite a range. So, what's the common thread among all these incredibly diverse examples then? What are the two defining properties that unite them all under this umbrella of matter?
The common thread, the unifying characteristic among all these things, is that they occupy space and possess mass.
Yeah.
In other words, they have both mass and volume. Without these two properties, something isn't considered matter in the scientific sense.
Okay, mass and volume. Got it. And when we talk about measuring these fundamental properties, mass and volume, what are the standard international units, the SI units that scientists use? And maybe for volume, are there other common units we should quickly recap? Units listeners might encounter in daily life.
Right, good point. For mass, the SI unit is the kilogram, or simply kg. That's our standard measure for the amount of stuff, basically, in an object. For volume, the FI unit is the cubic meter.
Yeah.
But you're absolutely right. For more everyday measurements, you'll often hear liter, or L. Just to put it into perspective, 1 liter is equivalent to 1 cubic decimeter,
Right.
dm. And it's also 1,000 milliliters,
Yeah.
ml.
Okay.
And 1 milliliter is equal to 1 cubic centimeter,
Mm.
cml. It's all about understanding how much space something takes up, you see.
It's pretty clear that humans have been observing and, well, pondering the nature of matter for a very, very long time. Can you shed some light on the historical perspectives, particularly from early Indian and ancient Greek philosophers? What did they believe matter was made of, and why does that ancient context still hold some relevance for us today?
What's truly fascinating here is how ancient minds across different cultures arrived at such similar profound insights.
Mhm.
Since ancient times, human beings have indeed been trying to understand the world around them. Early Indian philosophers, for instance, famously classified matter into 5 basic elements.
Tattva, right?
Exactly, the Panchtattva: air, earth, fire, sky, and water. Their belief was that everything, whether living or non-living, was fundamentally made up of these 5 elements. And what's interesting is that ancient Greek philosophers, completely independently, arrived at a very similar classification of matter.
Really? That's fascinating.
Yes, it shows a universal human curiosity and early scientific intuition across different cultures. It highlights that this fundamental questioning of what makes up the world is deeply ingrained in human nature, you see.
So those ancient classifications seem quite elegant, almost poetic in a way. But how does that connect to modern science? Have we completely abandoned those early ideas, or have they sort of evolved?
Oh, they've certainly evolved. Modern-day scientists have definitely moved beyond the Panchtattva, but the spirit of classification remains. Today, We classify matter in two primary ways, based on its physical properties,
Which we're focusing on today.
right, which we'll delve into today, and also its chemical nature, which involves how it reacts and transforms. That chemical aspect, while equally fascinating and building upon these fundamentals, is maybe a deep dive for another time.
Okay, understood. So, for our listener, when they go about their day, maybe picking up a fruit, feeling the breeze, seeing the clouds, what's the profound takeaway here? How are they interacting with these fundamental concepts without even realizing it?
Well, the profound takeaway is this. Every single interaction you have with the world, every touch, every breath, every glance, is an interaction with matter. When you pick up a piece of fruit or feel the breeze, you're not just experiencing a fruit or a breeze. You're directly engaging with these fundamental concepts of mass and volume and the underlying particles. Whether you consciously realize it or not, you're living, breathing, interacting in a world of matter. 2. The particulate nature of matter, not a solid block.
Okay, so we've established what matter is and its defining properties, mass and volume. But this leads us to an even more fundamental question about its structure, doesn't it? Is matter like one continuous, unbroken block, completely solid throughout? Or is it actually made of tiny, discrete pieces, almost like a cosmic Lego set? This seems like a crucial debate for understanding everything else.
That's a crucial question indeed. And it was actually a point of passionate debate for a very long time among scientists and philosophers. For a considerable period, two main schools of thought existed. One believed matter was continuous, much like a solid block of wood, smooth, unbroken, you see. The other proposed that matter was made up of particles, similar to how sand is composed of tiny grains. Imagine a smooth lump of clay versus a handful of sand. That was sort of the essence of the argument.
So, how did scientists finally settle this debate? Seems quite fundamental. The source mentions a very simple yet powerful activity involving water and salt or sugar. Can you briefly describe what happens in this experiment? And more importantly, what profound insight does it reveal about the true nature of matter?
Absolutely. This simple activity is quite elegant in how it helps us decide if matter is continuous or particulate. Imagine you take a beaker, fill it halfway with water, and carefully mark the water level. Then you add a spoonful of salt or sugar and stir it until it dissolves completely.
Okay, standard procedure. Now, what happens to the water level after the salt or sugar dissolves? And what are the key questions we should be asking ourselves during this observation?
Well, the key questions are, what exactly has happened to the salt? Where does it disappear to? And most importantly, for our debate, does the level of water change significantly? You'll observe that, surprisingly, the water level generally does not change significantly, if at all.
It doesn't, even though you added something.
Right. The salt or sugar doesn't just vanish, it disperses throughout the water.
And what's the inescapable conclusion from that simple observation? If the water level doesn't rise, what does that have to mean about the structure of water and salt?
The inescapable conclusion is that to explain why the water level doesn't rise, we must accept the idea that matter is made up of particles. The particles of salt or sugar have gotten into the tiny, invisible spaces that exist between the particles of water.
Ah, spaces between the particles.
Exactly. Think of it like adding small pebbles to a jar of sand. If there are spaces to fill, the overall volume doesn't increase dramatically. Figure 1.1 in the source illustrates this concept beautifully. When salt dissolves, its particles neatly fit into the vacant spaces within the water. This is your first aha moment, perhaps. Even seemingly solid or continuous liquids have hidden spaces within them.
That's a truly great visual thinking about those hidden spaces. Very clear. So for our listener, the next time they're stirring sugar into their coffee or salt into their soup, what profound reality are they witnessing firsthand?
So the next time you stir sugar into your coffee, you're not just mixing. You're witnessing direct, everyday evidence that both sugar and water are made of tiny, invisible particles. And crucially, that there are spaces in between them. It's quite profound when you think about it, the unseen world constantly at play. 3. The incredible smallness of matter's particles.
Okay, so we've established that matter is made of these discrete particles and there are spaces between them. Check. But this raises an even more mind-boggling question. How small are these particles? Are we talking about something we can just about see with a powerful microscope, maybe? Or are they so incredibly minute, so utterly tiny that they challenge our very imagination?
This is where it gets really interesting and truly astonishing. The particles of matter are incredibly, almost unimaginably small. They are on a scale that defies our everyday experience, and we can vividly demonstrate this with another simple yet incredibly powerful activity.
Okay, I'm intrigued. The source details a classic experiment with potassium permanganate. We don't need the full step-by-step, but could you describe the essence of this dilution activity? And more importantly, what breathtaking, almost unbelievable conclusion we can draw from it about the sheer, unfathomable smallness of these particles?
Certainly. The essence of this activity is to demonstrate extreme dilution. Imagine you take just 2 or 3 tiny, dark purple crystals of potassium permanganate, literally a pinch. You dissolve these in 100 milliliters of water, and you get a deep purple solution. Now here's the key part. You take just 10 milliliters of that solution and add it to 90 milliliters of fresh, clear water.
Diluting it 10 times.
Exactly. The color becomes lighter, naturally, but it's still distinctly visible. You then repeat this process. Take 10 milliliters from the new, lighter solution and put it into another 90 milliliters of clear water. You keep doing this, perhaps 5 to 8 times, systematically diluting it further and further.
Diluting it again and again.
Yeah.
Okay. And what's the key observation here? Even after diluting the solution so many times, what do we notice about the water's color? Does it just vanish?
That's the remarkable thing. Even after diluting the solution many, many times, you will notice that the water is still colored. Yes, the color becomes progressively lighter with each dilution, much fainter.
But it's still there.
It's still there. It stubbornly persists, showing its incredible ability to spread.
Wow. So what analysis and conclusion can we draw from this persistent spreading color even after such extensive dilution? What does it tell us about the sheer numbers and microscopic size of these particles? This seems like another huge aha moment.
This is indeed where the aha moment truly hits home. This experiment dramatically shows that even a mere few crystals of potassium permanganate have the power to color a vast volume of water, potentially up to 1,000 liters if you continue the dilutions long enough.
1,000 liters from just a few crystals.
Yes. This leads us to an inescapable conclusion. There must be millions, perhaps even billions, of tiny particles within just one of those potassium permanganate crystals. These particles are not static. They continue to divide themselves into even smaller and smaller groups of particles with each dilution, yet still carry the characteristic color. It's a testament to the staggering number of particles in what seems like a negligible amount of matter.
That's truly astonishing. Billions from just a few tiny crystals. Is there an alternative, maybe more common example we could use? If potassium permanganate isn't something our listeners might have at home.
Yes, absolutely. Good thinking. For those who might not have potassium permanganate, the same principle can be demonstrated using just, say, 2 milliliters of Dettol.
Ah, Dettol, okay.
You'll find that its distinctive smell can still be detected even after repeated dilutions. Just a tiny amount, you see, can permeate a huge volume. This further proves the particulate nature and their extreme smallness.
So what's the big overarching takeaway from all this about the scale of matter's particles? What should our listeners truly understand about their size?
The big takeaway, the profound truth, is that the particles of matter are truly, truly very small. They are small beyond our imagination.
Yeah.
This is a profound concept, really, making us appreciate that the microscopic world, invisible to our eyes, governs everything we see and experience.
Isn't that incredible? Just a few grains of something can influence 1,000 liters. It forces us to reconsider the emptiness around us. What does this reveal about the world we often take for granted, the world we can't see?
It reveals that there's an entire, bustling universe of tiny things interacting constantly, far too small for our eyes to see, yet profoundly impacting the macroscopic world we inhabit. It's like a hidden engine running everything, you see, always active. Forphy, characteristics of particles of matter, always moving, always interacting.
Okay, so we've learned that everything is made of these incredibly tiny particles and there are spaces between them. Now, let's explore their behavior. What are these tiny, tiny particles actually doing? Are they just sitting there passively, or are they constantly active, a hive of activity? What are their defining characteristics that fundamentally shape how all matter behaves around us?
Excellent question, because this is where matter truly comes alive, dynamically. These particles are far from static. They possess several crucial characteristics that govern the behavior of all matter. From the most solid rock to the most diffuse gas, it all comes down to these particle traits. Particles of matter have space between them. A deeper look.
Right. We touched upon this with the salt dissolving in water, the particles fitting into the spaces. But can you elaborate further on this fundamental idea that particles always have spaces between them? And maybe give us some more everyday examples to really solidify this concept in our minds.
Certainly. This characteristic is truly fundamental, as you said. Our initial activities with sugar, salt, or even dettol and potassium permanganate dissolving in water clearly showed that these substances distribute evenly throughout the water. This uniform distribution you see is only possible if the particles of one substance find vacant spaces to occupy within the particles of the other. If there were continuous blocks, like we discussed, this mixing wouldn't happen without significantly increasing the overall volume.
Makes sense. And beyond those specific experiments, what are some other very common everyday examples? Places where we unknowingly witness this intermixing and the presence of space between particles.
Think about making something as common as tea or coffee, or even a refreshing glass of Nimbu Padani, our homemade lemonade.
Ah, yes, Nimbu Pilani, perfect example.
Exactly. When you add sugar or milk to tea, or lemon juice and sugar to water for Nimbu Padani, the particles of one ingredient effectively intersperse themselves within the spaces between the particles of the other ingredients. The overall volume doesn't dramatically increase, does it?
No, not really.
Instead, the particles integrate perfectly, showing that there's always room for more at the microscopic level.
So, based on all these observations, what's the conclusive statement we can make about the presence of space within matter? Is it always there?
All these examples conclusively demonstrate that there is indeed enough space between the particles of matter, always. It's not empty space in the macroscopic sense, like a vacuum, but microscopic gaps between the constituent particles, you see. B, particles of matter are continuously moving, the role of kinetic energy.
Okay, so if these particles have space between them, are they just floating in place, stationary, or are they in constant motion, always moving? And how does something as ubiquitous as temperature factor into this movement? Does a change in temperature make a difference to this motion?
They are definitely on the move. This is a truly key characteristic. Particles of matter are continuously, incessantly moving, never still. This inherent motion means they possess what we call kinetic energy, the energy of movement.
Kinetic energy. Right.
And yes, this movement is directly and profoundly influenced by temperature. As the temperature rises, the particles gain more energy, causing them to move faster, more vigorously. Consequently, we can definitively say that with an increase in temperature, the kinetic energy of the particles also increases. It's like turning up the heat at a dance party, you see. Everyone starts moving faster.
Huh. Good analogy. So, how can we actually perceive or observe this constant movement, even though the particles themselves are far too tiny to see? The source suggests a simple incense stick experiment. Activity 1.3. What does this tell us about particle movement in the air?
This is a classic and very relatable demonstration. Imagine you place an unlit incense stick, an agarbati, in a corner of your room or classroom. You'll find you have to go quite near it, perhaps even right next to it, to perceive its faint smell.
Yeah, you have to get really close.
Right. Now, light the incense stick. What happens?
Ah, well, then you could smell it across the room.
Exactly. You can often smell the incense from a considerable distance away, without having to go close at all. This observation tells us that the particles of the burning incense, which are gases, are released into the air. They possess kinetic energy and move continuously, spreading throughout the space to reach your nostrils. The aroma doesn't just sit there, it travels.
Okay, that makes perfect sense for gases, but what about liquids? Do their particles move as well? And can we observe differences in their rate of movement? Activity 1.4 involving ink and honey and water sounds like it might reveal something interesting there. What do we observe?
Indeed, liquid particles also move, but their rate of movement can vary significantly. In this activity, imagine taking two separate glasses of water. Carefully add a single drop of blue or red ink along the sides of the first beaker, and similarly, add a drop of honey along the sides of the second. Then you simply leave both undisturbed in a corner.
Okay, ink in one, honey in the other. What happens immediately?
Immediately after adding ink, you'll see the color start to diffuse and spread quite quickly, almost like a plume spreading out. Immediately after adding honey, however, the honey will sink and remain largely localized for much longer before slowly starting to spread out. It's much slower.
Much slower for honey. And what about the long-term observation? How long does it actually take for the ink to spread evenly versus the honey? And what does that difference in speed highlight about liquids?
Well, how long does it take for the color of the ink to spread evenly throughout the water? Usually, maybe a few hours. For honey, it can take many hours, sometimes even days, to achieve an even distribution. Both eventually spread, confirming particle movement in liquids. But this clear difference in speed highlights factors like viscosity, how thick the liquid is, and the intermolecular forces, which affect how easily particles can move past each other and intermix. Honey is much more viscous, you see.
Got it. Viscosity plays a role. And to bring temperature back into the picture in a very direct way, how does adding a crystal to hot water versus cold water, as in Activity 1.5, help us understand the immediate impact of temperature on particle movement?
This activity vividly shows temperature's profound effect. You would drop a crystal of, say, copper sulfate or potassium permanganate into a glass of hot water, and drop another identical crystal into a glass of cold water. Importantly, you do not stir. You allow the crystals to settle at the bottom.
Okay, no stirring. What do you see then?
You'll observe the color slowly spreading upwards from the crystal in both glasses. As time passes, the color will eventually diffuse throughout the entire volume of water in both glasses. The crucial difference, however, is that the rate of mixing, or diffusion, is visibly and significantly faster in the hot water compared to the cold water.
Ah, so it spreads faster in hot water.
Much faster, yes.
So what does this striking difference tell us about the particles in both the solid crystal and the liquid water? And how does it explain the role of temperature in this diffusion process?
This directly illustrates that particles of both the solid crystal and the liquid water are moving. They're not static. The faster diffusion in hot water vividly confirms that the rate of mixing does change with temperature, specifically increasing with temperature. Why? Because the increased heat provides more kinetic energy to the particles.
More energy, faster movement.
Exactly. Making them move more vigorously, collide more frequently, and thus spread faster. It's all about that kinetic energy boost from the heat you see.
Right. So pulling together all these observations from the incense stick, the ink and honey, and the hot and cold water experiments, what can we definitively conclude about the movement of matter's particles? And what is the scientific term for this natural intermixing that we keep observing?
From these three activities, we can definitively conclude that particles of matter are continuously moving, ceaselessly in motion. They possess kinetic energy which increases with temperature. And this natural intermixing of different types of matter due to the movement of particles on their own is called diffusion.
Diffusion. Okay.
And we've consistently observed that on heating, diffusion becomes significantly faster, almost like a turbo boost for particle movement. See, particles of matter attract each other.
Now, here's a thought. If particles are constantly moving and have spaces between them, what stops everything from just flying apart into a chaotic mess? Like, why doesn't the table just disintegrate? Is there some kind of invisible glue or a fundamental force holding them together?
Indeed, there is, and that's a very important question. This is the third crucial characteristic, and it's what gives matter its cohesion. Particles of matter are not entirely independent entities. There is a force acting between them. This force of attraction is what keeps the particles together, preventing them from simply dispersing randomly. What's also profoundly important is that the strength of this force of attraction is not uniform.
Ah, it varies.
Yes, it varies significantly from one kind of matter to another. This variation, you see, is absolutely key to understanding why we have such distinct states of matter, solids, liquids, and gases.
Okay, the strength of attraction varies. The source proposes a rather fun analogy to demonstrate this. A game with human chains, Activity 1.6. How does playing this game help us visually understand the varying attractive forces between particles? Seems like a good way to picture it.
This is a brilliant analogy, actually, to make an abstract concept tangible and quite fun. Imagine you're playing this game in a field, forming human chains in different ways. The first group forms the strongest bond. Students hold each other from the back and lock arms tightly, much like traditional Idumishmi dancers. Maybe you've seen pictures.
Yes, I think so. Very tight formation.
Exactly. The second group forms a medium bond, simply holding hands, and the third group forms the weakest bond, just touching each other with their fingertips. Then a fourth group tries to run around and break these three human chains one by one into as many small groups as possible.
Okay, so what would be the key observations here? Which human chain would be the easiest to break and which the hardest? And what does that tell us by analogy about the attractive forces between actual particles?
You'd observe which group was the easiest to break, and clearly, it would be the group holding only with fingertips. They'd fall apart instantly.
Right, easy one.
Conversely, the group that was the hardest to break would be the Idumishmi dancers, with their tightly locked arms. You'd really have to pull hard there. This directly shows that the strength with which the particles, or students in this analogy, are held together varies. This is perfectly analogous to the varying forces of attraction between actual matter particles. The stronger the bond or force of attraction you see, the harder it is to pull them apart. It makes perfect sense visually.
Okay, that analogy helps. But beyond analogies, what about real, tangible materials? What happens when we physically try to break an iron nail? versus a piece of chalk, or maybe a rubber band as described in activity 1.7. What does this activity tell us about the comparative strength of attractive forces in these different substances?
This activity gives us concrete, real-world examples. Imagine you take an iron nail, a piece of chalk, and a rubber band. You then attempt to break each one using different methods, perhaps hammering the nail, snapping the chalk, or stretching the rubber band.
Okay, what would we find?
You'll find it incredibly difficult, almost impossible with your bare hands, to break the iron nail.
True.
The chalk will snap relatively easily with minimal force, and the rubber band will stretch significantly, deforming quite a bit before eventually breaking if enough force is applied. This directly tells us in which substance the particles are held together with greater force. The iron nail has the strongest attractive forces. Then perhaps the rubber band, which exhibits elasticity but still resists breaking. And then the chalk, which is quite brittle because its particles are held by weaker forces.
So the difficulty in breaking them relates directly to the force between particles.
Directly, yes.
And what about liquids? Can we cut liquids, for example, water? What does trying to cut water with our fingers, as described in activity 1.8, demonstrate about the cohesive forces within liquids?
This is a great way to test the forces within a liquid directly, and something everyone can try. To perform this, you simply take some water in a container and try to cut its surface with your fingers. Try to separate it.
Then what happens?
Your immediate observation would be that you are not able to easily cut the surface of the water and keep it separated.
No, it just flows back together.
It flows back together almost
Okay.
instantly. The reason for this phenomenon, you see, is due to the attractive forces between the water particles. These forces cause the surface of water to remain together. It resists being permanently separated by your fingers. It inherently wants to hold itself together. That's cohesion in action.
Cohesion. Okay. So pulling all three of these activities together, the human chain game, trying to break different substances, and even attempting to cut water. What's the overall undeniable conclusion they point to regarding the particles of matter?
These three activities strongly and consistently suggest that particles of matter indeed have a force acting between them, an attractive force. This force is absolutely crucial for keeping the particles aggregated, for holding them together, you see. And importantly, the strength of this force of attraction varies significantly from one kind of matter to another, which, as we said, directly leads us to understand the different states of matter. It's the underlying reason for solids, liquids, and gases behaving so differently.
Okay, so what's the significant implication for our listener here? Why should they care about the strength of these invisible forces beyond just a scientific concept? How does it affect their world?
Well, the significant implication is that the strength of these invisible forces is why you can hold a solid object like your phone or a pen. It's why water flows together into a stream or puddle rather than just atomizing into separate particles. And it's why a gas spreads out to fill its container, because the forces are too weak to hold it together. It's truly fundamental to how the entire world works, you see, dictating the very form and tangible behavior of everything around us. It explains why things are the way they are. V states of matter: solid, liquid, and gas.
Right. So we now know that all matter is made of these incredibly tiny, constantly moving particles that also attract each other with varying strengths. That's quite a picture emerging. Now, looking around, we see things in very distinct macroscopic forms. Things are hard, or they flow, or they're invisible gas. What are these different fundamental forms, these states of matter, and what fundamentally causes matter to exist in these various distinct states? Is it just those particle characteristics?
That's the next logical step in our deep dive, isn't it? Yeah. And yes, you're right. The differences in particle characteristics, their spacing, their movement, and their attractive forces, which we've just discussed, they directly give rise to the three main states of matter we observe all around us: solid, liquid, and gas. Matter, you see, exists in these three distinct states because the precise variation in the arrangement, movement, and attractive forces between its constituent particles. It's precisely why these states manifest so differently. It's all down to the particles.
Okay. Can you give us a quick verbal picture, almost like a visual aid, to help us imagine how the particles are arranged and behave in each of these three states? Perhaps referencing figure 1.5 from the source material to really nail down that underlying physics.
Yes, definitely. Imagine a magnified schematic of the particle arrangement, much like figure 1.5 would show. In solids, for example, the particles are very closely packed in fixed positions with very little space between them. They essentially just vibrate about their mean positions, like they're stuck in place but jiggling.
Okay, fixed and vibrating.
In liquids, particles are still relatively close, but they have enough energy and space to slip and slide over each other. That's what gives them fluidity.
Slipping and sliding. Right.
And finally, in gases, particles are far apart, moving randomly and rapidly throughout the available volume, with very large spaces between them, almost independent. This visual you see is absolutely key to understanding the underlying physics of each state. It's all about the particle's arrangement and energy. A. The solid state.
All right, let's begin our exploration of the states of matter with solids then. What makes a solid, well, solid? What are its defining, unmistakable characteristics that set it apart from liquids and gases?
Solids are, by far, the most rigid and structured state of matter. They have very specific properties due to their incredibly orderly particle arrangement and those strong attractive forces we talked about.
The source mentions activity 1.9, where we're asked to consider common items like a pen, a book, a needle, a wooden stick. Without going through the experiment step by step, what can we learn about the fundamental properties of solids by simply examining these objects? Maybe trying to change their shape or attempting to compress them.
By simply observing and interacting with these common items, we immediately highlight the key properties of solids. You'll observe that all these items have a clear, unchanging, definite shape. A pen is always pen-shaped.
Right.
They have well-defined boundaries, you see, and a fixed volume. A book is always a book-sized volume. When you try to compress them, try squeezing a pen, you'll find it very difficult, meaning they have negligible compressibility.
Yeah, you can't really squash them.
Exactly. Solids also have a strong tendency to maintain their shape even when subjected to an outside force. While they might break under excessive force, like snapping the stick, it's very difficult to change their fundamental shape. Thus, they are considered rigid. And generally, you won't see solids diffusing into each other easily at room temperature. They stay put.
Okay, that sounds very clear. Definite shape, fixed volume, rigid, incompressible. But what about those tricky examples that seem to bend the rules? They almost challenge our definition of a solid. Like a rubber band stretches dramatically. A pile of sugar or salt takes the shape of its container, and a sponge can be compressed quite easily. Are these really solids then, or do they force us to refine our understanding? This feels like an important clarification.
These are fantastic questions. They probe the nuances of the definition, and they are, in fact, still solids. But their unique macroscopic properties come from their very specific internal structures, you see. Let's take them one by one. The rubber band first. Yes, it changes shape under force when stretched, dramatically so. However, it crucially regains its original shape once that force is removed.
It bounces back.
It bounces back. If the force applied is too great, it breaks, which demonstrates the limits of its particle attraction. Its ability to return to its original state, this elasticity, makes it undeniably a solid.
Okay, that makes sense. So elasticity doesn't disqualify it. What about sugar and salt then? They certainly appear to take the shape of any jar or plate they're poured into.
That's a good point about appearance. With sugar and salt, while a pile of them appears to take the macroscopic shape of the jar, plate, or even your hand, the crucial point is that the shape of each individual sugar or salt crystal remains fixed. Each tiny crystal is a solid with a definite shape.
So the individual crystals are still solid shapes.
Precisely. The macroscopic shape you observe is simply an aggregate, a collection of many, many individual tiny solids, each retaining its own definite shape.
Okay, I see the distinction. And the sponge, we can compress that so easily. How does that fit the definition of a solid, given its apparent squashiness?
The sponge. Yes, a sponge is indeed a solid, yet it's seemingly compressible. Why? It has minute holes or pores within its solid structure. These pores are filled with air.
Full of air pockets.
Exactly. When you press a sponge, you're essentially expelling this trapped air, allowing the solid framework to temporarily deform and compress into that empty space. Once the pressure is released, the air rushes back in and it regains its shape. The solid material itself, you see, isn't being compressed. The air within its pores is being pushed out.
Fascinating. So the solid structure is still there. Now, how do the particle characteristics we discussed earlier, the tight packing, the strong attractive forces, the limited vibrational movement, connect directly to these defining properties of solids, like their definite shape, rigidity, and negligible compressibility?
It connects directly. In solids, the particles are truly tightly packed. The attractive forces between them are at their maximum, holding them firmly in place, and there's very little space available between them. They're essentially in fixed positions and can only vibrate about their mean positions. This rigid arrangement and strong interparticle attraction is precisely what gives solids their definite shape, distinct boundaries, and their characteristic rigidity and incompressibility.
See.
The liquid state.
Okay, so solids are all about rigidity and fixed forms thanks to those tightly packed, strongly attracting particles. What about liquids then? They seem so different. They flow, they adapt, almost chameleon-like to their surroundings. What are the unique characteristics that fundamentally set them apart from solids?
Liquids, you see, represent an intermediate state. They sit between the rigidity of solids and the freedom of gases. Their particles have more freedom of movement than in solids, but they're still relatively close to each other, maintaining a certain degree of cohesion.
The source describes activity 1.0, which involves collecting various liquids in different shaped containers. Without listing every step, what do we discover when we pour these liquids into different containers or observe what happens if they're spilled? What does this reveal about their shape and volume?
This activity clearly demonstrates the fluid nature of liquids. Imagine you collect water, cooking oil, milk, some juices, maybe a cold drink, and you gather containers of different shapes, say a tall, narrow beaker, a wide, shallow dish, maybe even a round flask. You'd measure, say, 50 milliliters of one liquid using a measuring cylinder and transfer it into each container one by one.
Okay, pouring the same amount into different shapes.
Right. You'd immediately observe that liquids do not have a fixed shape. Instead, they readily take up the shape of the container in which they are kept. The water takes the shape of the flask, the dish, the beaker.
But does the amount change? The volume?
That's the crucial point. They do have a fixed volume. That 50 milliliter remains 50 milliliter, regardless of the container shape. Liquids flow and change shape easily because of this particle arrangement. They're not rigid, but we can accurately call them fluid.
Fluid, okay. Not rigid, but fluid.
Yes. And if spilt, they simply spread out, confirming they don't hold their own shape against gravity, for example.
Right. Now, you mentioned diffusion earlier. Does this intermixing of particles happen in liquids as well, like we saw with salt and sugar and water? And what about gases dissolving in liquids? Is that an important aspect of their nature? Can gases get into liquids?
Yes, absolutely, and this is extremely important, especially for life on Earth. We've already seen from activities like the ink in honey or crystals in water that solids and other liquids can diffuse into liquids they mix. But crucially, gases from the atmosphere also diffuse and dissolve in water.
Gases like oxygen.
Exactly. Think about oxygen and carbon dioxide. These dissolved gases are absolutely essential for the survival of aquatic animals and plants. All living creatures need to breathe, right? And aquatic animals can breathe underwater precisely because of the dissolved oxygen in the water. Without that diffusion of gases into water, you see, underwater life as we know it simply wouldn't exist. It's vital.
Wow, that's a really important point. So if I'm following, we can conclude that solids, liquids, and gases are all capable of diffusing into liquids. And what about the rate of diffusion in liquids compared to solids? Is there a noticeable difference, and why? Is it faster in liquids?
That's right. We can conclude that solids, liquids, and gases are all capable of diffusing into liquids. Furthermore, the rate of diffusion in liquids is significantly higher than that in solids. It happens much faster.
Why is that?
This is directly due to the particle characteristics we've been discussing. In the liquid state, particles move much more freely and have greater spaces between them as compared to particles in the solid state. This greater freedom and spacing allow for much easier and faster intermixing, or diffusion, you see. They can jostle past each other more easily.
Okay, that makes sense. More freedom, faster mixing. So how do the particle characteristics in liquids specifically, their less tight packing, weaker attractive forces compared to solids, and ability to slip and slide explain their observed properties, like their fluidity and lack of definite shape, while still managing to maintain that fixed volume?
It explains it perfectly. In liquids, particles are less tightly packed than in solids. The attractive forces are weaker, which provides enough give for particles to slip and slide over one another. This gives liquids their characteristic fluidity and their lack of a definite shape as they conform to their container. However, the attractive forces are still strong enough to keep them relatively close together, preventing them from flying off entirely, which is why they maintain a fixed volume. It's a delicate balance, you see, between freedom and cohesion. Enough attraction to keep volume, enough freedom to flow. C, the gaseous state.
All right, and finally, we arrive at gases, the third major state. We often can't even see them, yet they're absolutely everywhere, defining so much of our environment, like the air we breathe. What fundamentally defines a gas? And how do its particles behave so differently, so much more freely than those in solids and liquids?
Gases, you see, are the most energetic and least structured state of matter. They are fundamentally defined by an incredible degree of particle freedom and truly vast spaces between them. They're the rebels of the particle world, you could say.
Ha! Rebels. I like that.
Yeah.
Have you ever noticed a balloon seller, perhaps at a fair or on the street, filling a large number of balloons from a single, relatively small cylinder of gas? What does this common observation immediately hint at regarding a key property of gases that sets them apart?
That's an excellent everyday observation that tells us a great deal. This common sight already hints at a key property of gases, specifically their remarkable compressibility.
Compressibility.
Yes, and also their ability to expand to fill a large volume from a much smaller container. You might wonder how so many balloons can be filled from that one small cylinder. It's precisely due to this property you see. The gas is squeezed in there.
Okay, compressibility. To understand gases better, the source suggests an activity using syringes filled with different substances. Activity 1.1. Without getting into the full procedural details, what do we learn about gases, liquids, and solids when we try to compress them in this manner? What's the stark contrast we observe?
This activity vividly demonstrates this defining feature of gases, their high compressibility. Imagine you have three identical syringes. One is simply filled with air, which is a gas. The second is filled with water, liquid, and the third contains small pieces of chalk, a solid. The nozzles are sealed. Now, if you try to push the piston into each syringe, attempting to compress its contents,
What happens? Is it easy or hard?
what you'll observe is that the piston is easily pushed in when the syringe contains gas. The air compresses almost effortlessly. You can push it quite far. It's very difficult to push the piston for water, the liquid. It barely moves. And it's practically impossible for the chalk pieces, the solid. No movement at all. This experiment clearly shows that gases are highly compressible as compared to solids and liquids. There's lots of space to squeeze them into.
That's a very clear demonstration. Where do we see this high compressibility of gases applied in the real world, in our daily lives, particularly regarding things like energy and medicine? What are some practical benefits of this property?
Oh, there are many real-world applications all around us. The liquefied petroleum gas, or LPG, cylinder in your home for cooking.
Yes, the LPG cylinder.
It contains highly compressed gas, stored as a liquid under pressure. Oxygen supplied to hospitals for medical use is also compressed gas in cylinders. And compressed natural gas, or CNG, is now widely used as fuel in vehicles these days.
Right, CNG cars.
Exactly. The significant benefit here you see is that due to high compressibility, large volumes of a gas can be compressed into a small cylinder. This makes it easy to store and transport them, making them incredibly practical for everyday use in various industries. It's a game changer for storage and transport, really.
Very practical indeed. Now, we talked about diffusion in liquids, how particles intermix. What about gases? How does that explain why we often smell hot food cooking from another room so quickly? It seems almost instantaneous sometimes.
This is another excellent example of particle movement and diffusion in powerful action, especially in gases. We often know what's cooking in the kitchen without even entering, right? Simply by the aroma reaching our nostrils within seconds.
Yes, definitely happens.
The particles of the aroma of food, which are gases, mix incredibly rapidly with the particles of air. These mixed particles then spread quickly from the kitchen, traversing the rooms, reaching us, and even farther away in a matter of seconds. If you compare this speed with the rate of diffusion in solids and liquids, gases diffuse much, much faster.
Why so much faster?
This is due to the very high speed of gas particles and the enormous spaces between them. This allows them to intermix very quickly and travel great distances without bumping into things too much.
Okay, high speed, large spaces lead to fast diffusion. Makes sense. Now, if these gas particles are moving so incredibly fast and randomly bouncing around all over the place, do they just harmlessly collide, or do they actually exert any measurable force? Perhaps something we experience as pressure, like inside that balloon or cylinder.
Oh, they absolutely exert a measurable force, and we most certainly perceive and use this as pressure. In the gaseous state, particles move about randomly at incredibly high speeds, as we said. Due to this constant random movement, these particles frequently hit each other and, crucially, also collide with the walls of the container they are in.
Banging against the walls.
Constantly banging against the walls. The force exerted by these constantly moving gas particles per unit area on the walls of the container is precisely what we define as the pressure exerted by the gas. It's the cumulative effect of countless tiny impacts you see, adding up to a noticeable force.
Right, the combined effect. So how do the particle characteristics of gases, their immense spacing, their negligible attractive forces, and their incredibly rapid random movement explain all these observed properties? Things like high compressibility, rapid diffusion, and the exertion of pressure. It all ties back to the particles.
Absolutely, it all ties back. In gases, the particles are very far apart. The attractive forces between them are minimum, almost negligible, so they barely interact. And there are truly vast spaces between them. They move completely randomly and at very high speeds. This combination directly leads to their high compressibility, lots of space to squeeze into, their rapid diffusion, easy movement, and the exertion of pressure on container walls due to their constant energetic collisions. It's all interconnected at the particle level. The behavior explains the properties.
Okay, fantastic. So, from the air in your car tires keeping them firm to the wonderful smell of your favorite curry wafting from the kitchen, what does understanding these fundamental gas properties help our listeners truly appreciate in their daily lives?
Understanding gas properties helps you appreciate the invisible, yet powerful, forces and movements at work all around you every single day. It gives you a profound insight into why these everyday phenomena occur, connecting the microscopic world of particles, which we can't see, to your tangible daily experience. It demystifies things a bit, you see. 6. Can matter change its state? The dance of temperature and pressure.
Right. We've now thoroughly explored solids, liquids, and gases, understanding their unique particle behaviors and properties. Very clear. But we know from everyday experience, don't we, that things don't always stay in one state. Water is the perfect example. It can be ice, then liquid water, and then steam. So the big question is, can matter actually change its state? And what are the fundamental forces or triggers that drive these incredible transformations? How does ice become water?
That's where the dynamism of matter truly shines, isn't it? The answer is a resounding yes. Matter can absolutely change its state. Water is a perfect everyday example of this versatility, a substance we all interact with in all three forms routinely. We all know from observation that water can exist in three states:
Yeah.
as ice in its solid form,
Solid.
as the familiar water we drink in its liquid form,
Liquid.
and as water vapor or steam in its gaseous state,
Gas.
solid, liquid, gas, all the same substance, water.
So, when a substance changes its state, say from ice to water, or water to steam, what fundamentally happens inside the matter? What goes on at the particle level during these transformations? How does the change actually take place?
These are the underlying questions we need to answer to truly understand these shifts. We need to investigate what happens at the particle level, how their energy changes, how their spacing changes, how the effect of attractive forces changes,
Hmm.
and we need to understand the precise mechanisms driving these changes, what makes them happen.
A.
Effective change of temperature.
Okay, let's tackle temperature first, as it's such a common catalyst for change we see all the time. Heating things up, cooling things down. How exactly does increasing temperature, for example, turn solid ice into liquid water? What's going on at the particle level that causes this process we call melting?
Temperature is indeed a primary, immensely powerful driver for state changes. When we're talking about melting, or the solid-to-liquid conversion, it's all about increasing the kinetic energy of the particles by adding heat.
Okay, adding heat increases kinetic energy. The source describes an experiment, Activity 1.12, Part 1, heating ice in a beaker, shown in Figure 1.6a. What are the truly critical observations we make, particularly regarding the temperature when the ice starts melting? And then crucially, what happens to the temperature reading while all the ice is converting into water? Does it keep rising?
This experiment reveals a counterintuitive but absolutely fundamental principle. Imagine you take about 150 grams of ice in a beaker and suspend a laboratory thermometer, ensuring its bulb is in contact with the ice. You then start heating the beaker gently on a low flame. You'd note the temperature when the ice starts melting, usually 0 degrees C or 273 Kelvin.
Okay, 0 degrees Celsius.
And then you keep watching the thermometer as all the ice converts into water.
So what's actually happening at the particle level as the ice melts? How does the heat affect them?
As we increase the temperature of a solid like ice by adding heat, the kinetic energy of its particles increases significantly. Due to this increased kinetic energy, the particles start vibrating with greater speed and amplitude around their fixed positions. They jiggle more intensely.
Okay, more vigorous vibration.
The energy supplied by the heat eventually becomes sufficient to overcome those strong forces of attraction that hold the particles in their rigid, fixed solid arrangement. The heat energy breaks the bonds, essentially.
Breaks the bonds, or weakens them enough.
Weakens them enough for the particles to move more freely, yes. At this critical point, particles begin to leave their fixed positions and start moving more freely, sliding past each other. A stage is reached where the solid completely melts and transforms into a liquid.
And how do we precisely define the melting point then? What does this specific temperature tell us about the substance itself? And what's another scientific term for this process of melting?
The minimum temperature at which a solid melts to become a liquid at atmospheric pressure is called its melting point. This specific temperature you see is a direct and powerful indication of the strength of the force of attraction between the particles of that solid. Stronger forces mean a higher melting point.
Makes sense.
For ice, as we said, the melting point is 273.15 Kelvin, which is commonly known as 0 degrees C. The process of melting, or the change from a solid state into a liquid state, is also scientifically known as fusion.
Fusion. Okay. Now, this is absolutely fascinating, but here's something that always puzzled me, and maybe your listeners too. If the ice is melting, we're continuously adding heat, right? The flame is still on. So why does the temperature of the entire system remain constant during the melting process? It stays at 0 degrees C, even though we're still supplying heat. Where does all that heat energy go? Is it truly hidden somehow? This feels like a huge aha moment if we can crack this mystery.
This is indeed a crucial hidden aspect and a major aha moment, as you
Yeah.
say. You will observe that the thermometer reading does not change after the melting point is reached. It remains stubbornly constant at 0 degrees C until all the ice is melted into water, even though we continue to heat the beaker.
So the heat is going in, but the temperature isn't rising.
Exactly. This supplied heat energy is not used to raise the temperature, meaning it's not increasing the kinetic energy of the particles. Instead, it gets entirely used up in changing the state of the substance itself. Specifically, by overcoming those forces of attraction between the particles, allowing them to break free from their fixed solid positions and move more readily in the liquid state. Because this heat energy is absorbed by the ice without showing any rise in temperature on the thermometer, it's considered to be hidden within the contents of the beaker. This is precisely known as latent heat. The word latent itself, you see, means hidden.
Latent heat, the hidden heat. Wow. So how do we specifically define this latent heat of fusion then? And what's the profound implication for particles in liquid water versus particles in ice, both at the exact same temperature, 0 degrees CO? Does one possess more energy than the other?
Specifically, the amount of heat energy that is required to change 1 kilogram of a solid into its liquid state at atmospheric pressure at its melting point is known as the latent heat of fusion. This has a very significant implication. Particles in water at 0 degrees C, 273 K, actually possess more energy than particles in ice at the exact same temperature.
More energy even at the same temperature.
Yes, because they have absorbed this additional latent heat of fusion to change their state, to break those bonds without increasing their kinetic energy temperature. They hold that extra energy internally.
Okay, that's a crucial concept. Latent heat of fusion. So ice becomes water through melting and absorbing this latent heat of fusion.
Got it. Now, what about turning that liquid water into a gas, like steam? How does that process, which we call boiling, work? And how does temperature continue to influence it, pushing particles into an even more energetic state?
The process from liquid to gas is similar in principle, but it involves the particles absorbing even more energy, giving them far greater freedom to escape entirely. Right, so after the ice melts, the activity, part 2 of activity 1.12, figure 1.6b, continues to hit the water. What do we see as the water starts boiling vigorously and turns into vapor or steam? What's happening at the particle level then to cause this dramatic change?
You would continue heating the beaker, perhaps stirring with a glass rod, until the water starts boiling. You'd see bubbles forming. You'd keep a careful eye on the thermometer until most of the water has vaporized. When we continue to supply heat energy to the water, now in its liquid state, its particles start moving even faster and more vigorously.
Even faster than in melting.
Much faster. At a certain critical temperature, the boiling point, a point is reached where the particles have sufficient energy to completely break free from the attractive forces of each other. Not just to slide past, like in melting, but to escape entirely into the surrounding atmosphere as a gas. At this temperature, the liquid begins to change rapidly and dramatically into a gas.
And how do we formally define the boiling point? And why is boiling considered a bulk phenomenon rather than just something happening at the surface, like evaporation, which we'll discuss later? What does bulk mean here?
The temperature at which a liquid starts boiling at the atmospheric pressure is known as its boiling point. For water, this temperature is 373 K, which is of course 100 degrees C. It's considered a bulk phenomenon because particles from the bulk, that is, the entire volume of the liquid, not just those at the surface, gain enough energy to change into the vapor state. The bubbles you see forming within water, you see, are water vapor forming throughout the liquid, not just on top. That's the bulk aspect.
Ah, the bubbles come from inside. Got it. Bulk phenomenon. And again, that question about temperature. Does the temperature remain constant during boiling, just as it did during melting? Does it stay at 100 degrees C? And what is this latent heat of vaporization that the source mentions? Is it similar to latent heat of fusion?
Yes, a very similar phenomenon occurs here as well. Particles in steam, or water vapor, at 373 K, 100 degrees C, actually possess more energy than liquid water at the exact same temperature.
Again, more energy at the same temperature.
Yes, this is because these particles in steam have absorbed extra energy, again in the form of latent heat of vaporization. Following the definition of latent heat of fusion, the latent heat of vaporization is the amount of heat energy required to change 1 kilogram of a liquid into a gas at atmospheric pressure at its boiling point. It's that hidden energy required for the complete phase change from liquid to gas, you see. Takes energy just to make the jump.
Okay, latent heat of fusion for melting, latent heat of vaporization for boiling, very important. Just a quick recap on temperature units again, as we've used both Celsius and Kelvin throughout. For our listeners who might need a quick refresher, how do we typically convert between them? Just the simple way.
A quick mental note on temperature conversion. Kelvin, or K, is the SI unit, often preferred in scientific contexts. To convert Celsius to Kelvin, you simply add 273. So 0 degrees C is 273 K, 100 degrees C is 373 K. And conversely, to convert Kelvin to Celsius, you subtract 273. We often round 273.15 K to 273 K for convenience in general calculations, as we have done here.
Perfect, thanks. So the standard path is solid to liquid, then liquid to gas with heating. But is there any way for matter to completely skip the liquid phase? Can it jump directly from a solid state to a gaseous state? This sounds like a magical shortcut. Does that ever happen?
Indeed there is, and it's a truly fascinating phenomenon called sublimation. While most substances follow the solid liquid to gas path when heated, some unique substances exhibit this direct change from the solid state to the gaseous state, and vice versa, without ever passing through the liquid phase. It is like a direct teleportation for particles, you see, skipping the middle step entirely.
Sublimation. Okay, direct solid to gas. The source describes heating camphor in activity 1.32, shown in figure 1.7. What visually happens during this process, and what does it directly demonstrate about these amazing direct state changes?
This activity provides a clear visual example of sublimation. Imagine you take some camphor crystals, kapur, as we call it.
Yes, kapur, used in puja often.
Exactly. You crush them slightly and place them in a china dish. Then, you place an inverted funnel over the china dish, ensuring its rim sits snugly, and you plug the stem of the funnel with cotton to close the opening. Now, you heat the china dish slowly from below and carefully observe what happens.
What do we see? Does it melt?
No. You will observe that the solid camphor directly converts into vapors. You might see fumes rising. These vapors then, upon encountering the cooler inner walls of the inverted funnel, cool down and condense back into solid camphor without ever forming a liquid. Solid to gas, then gas back to solid on the cooler surface.
Wow, no liquid involved at all. So we define that direct jump from solid to gas as sublimation. What about the reverse process, a gas turning directly back into a solid, like the camphor on the funnel? Does that have a specific name too?
Yes, this direct change of state from a solid to a gas without passing through the liquid state is, as we said, called sublimation. Conversely, the direct change of a gas to a solid without changing into the liquid state is called deposition. So the camphor vapor undergoes deposition on the funnel.
Sublimation and deposition. Got it. Is there an everyday example of sublimation that our listeners might be familiar with, something they might have witnessed in their own homes, perhaps?
Absolutely. Think of naphthalene balls or mothballs, which many of us use in our wardrobes or trunks to protect clothes.
Ah, yes, the white mothball.
Exactly. Over time, these mothballs simply disappear, don't they? They shrink and vanish.
Yeah, they do, without leaving any liquid residue.
Precisely. That's sublimation in action, you see. The solid naphthalene is directly turning into a gas and dispersing into the air. B, effective change of pressure.
Okay, we've seen how dramatically temperature changes the state of matter, melting, boiling, even sublimation. But does pressure also play a significant role? Can we, for example, force a gas into a liquid state just by squeezing it incredibly hard? Does pressure matter?
Absolutely. Pressure is equally critical, alongside temperature, in determining the state of matter. Especially for gases. We've already learned that the fundamental differences in the various states of matter are due to the differences in the distances between their constituent particles.
Right, the spacing.
So what happens when we start putting significant pressure on and compressing a gas enclosed in a cylinder, like in figure 1.8? The particles are forced closer and closer together, reducing those vast spaces between them.
Squeezing them together.
Exactly.
So it is possible to liquefy gases just by applying pressure
Hmm.
and maybe cooling them too. And where do we see this clever application in our homes and industries? We mentioned LPG and CNG before.
Yes, precisely. By applying significant pressure and often simultaneously reducing the temperature, which slows the particles down, we can indeed liquefy gases. We force the particles close enough for the weak attractive forces to take hold. This is exactly how LPG liquefied petroleum gas in your kitchen cylinder is stored, as a liquid under high pressure. Similarly, oxygen in hospital cylinders or nitrogen used in various industries are all stored as compressed liquids.
So pressure can turn gas into liquid. Now, we've all heard of dry ice, that fascinating substance used for dramatic fog effects in movies or concerts. How does dry ice directly relate to the effect of pressure on matter? And why is it called dry? This seems like another aha moment illustrating pressure's power.
Dry ice is a perfect example of pressure's profound influence. Solid carbon dioxide, or KO, yours is what dry ice is, it's stored under very high pressure.
Okay, solid CO2 under high pressure.
Now, when that pressure is dramatically decreased, say, you just take it out into the open air down to 1 atmosphere, which is simply our normal atmospheric pressure at sea level. The solid CO gets converted directly into its gaseous state without ever passing through the liquid state. It sublimes.
It sublimes instantly when the pressure drops.
Exactly. This is precisely why it's called dry ice. It doesn't melt into a puddle of liquid. It just turns straight into invisible Key-Oats gas. That's a wonderful demonstration, you see, of how pressure can directly dictate state changes. High pressure keeps it solid. Low pressure lets it sublime.
Fascinating. Dry ice makes sense now. And just to clarify, we've mentioned atmosphere as a unit of pressure. What is the standard SI unit for pressure, and what's its approximate relation to 1 atmosphere?
Good to clarify units. Remember, an atmosphere, or atterohm, is a common unit for measuring gas pressure. The SI unit of pressure is Pascal, or Ca,
Mm-hmm.
and 1 atmosphere is approximately 1.01 pascals. So quite a lot of pascals in 1 atmosphere. Our normal atmospheric pressure at sea level is taken as 1 atmosphere, or about 101,000 pascals.
Okay, pascals, got it. So what's the overall encompassing conclusion we can draw about the interplay between pressure and temperature? How do these two factors ultimately determine the state of matter, as visually summarized in Figure 1.9? Are they the main controls?
The overall conclusion you see is that the interplay between pressure and temperature ultimately determines the state of a substance. Whether it will be a solid, a liquid, or a gas depends on both these conditions. These two factors are like the essential dials on a control panel, allowing us to change matter's form by manipulating the balance between particle attraction and kinetic energy. Increased temperature, particles move more. Increased pressure, particles get closer.
Temperature and pressure, the two key dials. So the reason you can inflate a tire so firmly, keeping its shape under the car's weight, or witness clouds forming high above where it's colder and pressure is different, it isn't just magic. What's actually happening at the fundamental level?
It's the meticulous, intricate dance of temperature and pressure dictating the state of matter all around you. It's these fundamental principles at work, silently shaping our environment, enabling technology like refrigeration or pressure cookers, and creating natural phenomena like clouds or dew. It's physics in action.
Cooling from the surface.
Okay, so far we've talked about changing states by heating a liquid all the way to its boiling point, 100 degrees C for water, or by applying significant pressure, like with LPG or dry ice. But what about everyday phenomena like wet clothes drying on a line, or a puddle disappearing on a warm, sunny day, even if it's not 100 degrees out? The water turns into vapor, but it's clearly not boiling. What's going on there? This isn't the same as boiling, is it?
That's an excellent observation, and you're absolutely right, it's not boiling. This brings us to a crucial and very common phenomenon called evaporation. It's a distinct state change from liquid to vapor that happens below the boiling point. It's a much more subtle and continuous process.
Evaporation. Okay, different from boiling. Can you give us a clearer definition of evaporation then, explaining exactly what's happening at the particle level to make it different from boiling? And why is it specifically considered a surface phenomena?
Certainly. We see everyday examples of evaporation all the time. Water, when left uncovered in a glass, slowly diminishes, changes into vapor. Wet clothes left out dry up eventually. Now, we already know that particles of matter are always moving and are never at rest, even in liquids. They have kinetic energy. In any given liquid at any temperature, there are particles with varying amounts of kinetic energy. Some are moving faster, some slower.
A range of energies.
Exactly, a distribution. In liquids, you see, a small fraction of particles located right at the surface happen to have higher kinetic energy than the average. They're the faster ones near the top. These energetic surface particles are able to overcome the forces of attraction from other particles in the liquid just enough.
Just enough to break free.
Just enough to break free and escape into the surrounding atmosphere as vapor. This phenomenon, this change of a liquid into vapors at any temperature below its boiling point, is called evaporation. And yes, it is distinctly a surface phenomenon because only those energetic particles at the very top have a chance to escape directly into the air. Particles deep inside can't just leave.
Only the ones at the surface. Okay, that makes sense. Evaporation is a surface thing. Factors affecting evaporation. So if evaporation is happening all the time silently at the surface, what makes it happen faster or slower? What are the key factors that significantly influence its rate? Factors that we might even observe in our daily lives when drying clothes, for example.
There are four main factors that significantly affect the rate of evaporation, and yes, we can indeed observe them through very simple everyday occurrences.
Okay, four factors. The source proposes an activity 1.12, with water in test tubes in china dishes, placed in different locations and observed on different days. We don't need the step-by-step instructions, but what crucial insights does this activity provide about these factors influencing evaporation? What variables are they testing?
This activity helps us understand the crucial variables at play. Imagine observing water evaporating from different containers, maybe a narrow test tube versus a wide open china dish. That tests surface area. Then placing them in different environments near a fan, wind, by a window on a warm day, temperature, or inside a cool cupboard, lower temperature, less wind, and then perhaps repeating this on a humid, rainy day versus a dry day, humidity. From these kinds of observations, you'll infer the following key factors and their effects.
Okay, let's take the first one, surface area. Why do we instinctively spread out wet clothes to dry rather than leaving them in a crumpled heap? How does that relate to evaporation?
It relates directly. Because evaporation is a surface phenomenon, you see. If the surface area exposed to the atmosphere is increased by spreading out clothes, for example, a larger number of liquid particles are at that exposed surface.
More particles at the starting line.
Exactly. More particles are in a position to potentially gain enough energy to escape as vapor. Thus, the rate of evaporation increases significantly. Spreading clothes out is a perfect, practical application of this principle. More surface, faster drying.
Makes perfect sense. Second factor, temperature. Why do clothes dry so much faster on a hot, sunny day compared to a cooler one? That seems obvious, but why?
With an increase in temperature, more particles of the liquid gain enough kinetic energy, that energy of movement. More particles reach that threshold energy needed to overcome the attractive forces holding them in the liquid state and transition into the vapor state.
So higher temperature means more particles can escape.
Precisely. This directly and dramatically increases the rate of evaporation, which is why things dry quicker on a hot day. The particles are simply more energetic on average.
Okay, third factor, humidity. What exactly is humidity in scientific terms? And how does a humid day affect the rate at which things dry? Why do clothes take so long to dry on a rainy day, for instance? Feels sticky too.
Humidity is simply the amount of water vapor already present in the air around us. The air around us, you see, can only hold a definite maximum amount of water vapor at a given temperature. It has a saturation point.
Like a sponge that can only hold so much water?
Exactly like that. If the amount of water vapor in the air, the humidity is already very high, the air is essentially more saturated, closer to being full, and so it has less capacity to take on more water vapor from the evaporating liquid. The sponge is already damp, so the rate of evaporation decreases significantly. This is precisely why things dry so slowly on a rainy, humid day. The air is already full of water vapor.
Less room for more vapor in the air.
Got it.
And fourth, the last factor, wind speed. We've all noticed clothes drying much faster on a windy day compared to a still one. Why does an increase in wind speed have this effect?
It's a very common observation, isn't it? Clothes dry much faster on a windy day. With an increase in wind speed, the particles of water vapor that have just evaporated from the liquid surface are quickly carried away with the wind.
The wind blows them away.
Yes, it blows away that layer of humid air right next to the wet surface. This decreases the amount of water vapor in the immediate surroundings of the liquid. It maintains a steeper concentration gradient, you see, between the liquid surface and the air further away. This allows more liquid particles to evaporate more quickly into the now drier immediate air. The wind essentially clears the space for more evaporation to occur efficiently.
So, surface area, temperature, humidity, and wind speed. The four key factors. B, how does evaporation cause cooling? Okay, this is truly amazing. We understand evaporation better now. But here's something that always feels counterintuitive, but we experience it. Can evaporation actually make things feel cold? Like when we put certain liquids like spirit or petrol on our palm, it feels instantly cold. Or when our body sweats to cool down. How does this seemingly simple process of a liquid turning into a gas actually cause a cooling effect? Where does the cold come from?
Yes, this is one of the most remarkable and profoundly useful consequences of evaporation. It causes a cooling effect. And you're right, we feel it often. The mechanism of cooling is quite elegant, really. In an open vessel or on any exposed surface like your skin, the liquid is continuously evaporating. Now, for the particles at the surface to gain enough energy to escape as vapor to make that jump, they must absorb this required energy from their immediate surroundings or from the surface they are on, like your skin.
They take energy from the surroundings.
Yes. They absorb heat energy from whatever they are touching. This absorption of energy from the surroundings effectively makes those surroundings lose heat and therefore feel cold. The energy they absorb, you see, is precisely the latent heat of vaporization we discussed earlier, needed for the state change. They steal heat to evaporate.
Ah, they steal heat from our skin, making it feel cold. That's the cooling effect.
Exactly. That's the essence of evaporative cooling.
Can you give us some more everyday examples of this cooling due to evaporation? For instance, why does our palm feel instantly cold when we put acetone, like nail polish remover or maybe perfume or surgical spirit on it?
Absolutely. The particles of acetone or petrol or perfume or spirit are highly volatile. They evaporate very easily. They gain energy rapidly from your palm or the immediate surroundings. As they quickly evaporate, they take this absorbed energy, this latent heat, with them into the air, leaving your palm feeling distinctly cool because it has lost heat energy. It's a very direct experience of cooling by evaporation.
Okay, and what about that common practice in hot climates, especially in villages maybe? Why do people often sprinkle water on roofs or open ground after a scorching sunny day? How does that simple act cool things down?
The reason for this, you see, is that water has a remarkably large latent heat of vaporization. It takes a lot of heat to evaporate water. As the sprinkled water evaporates from the hot roof or ground, it absorbs a significant amount of heat energy from that hot surface. This absorption helps to cool the surface down considerably, making the surroundings feel much cooler. It's a very effective natural air conditioner.
Using water's high latent heat. Clever. And during the peak of summer, why are cotton clothes so widely recommended? We wear cotton kurtas, cotton shirts. How does this connect to our body's natural cooling mechanism and the process of evaporation?
During summer, our body naturally produces more sweat or perspires. This is a natural built-in mechanism to keep us cool.
Right, sweating cools us down. But how?
We know that during evaporation, the particles at the surface of the sweat gain energy from our body surface and change into vapor. The heat energy equivalent to the latent heat of vaporization is absorbed directly from the body.
Our body provides the heat for sweat to evaporate.
Exactly, which effectively leaves the body feeling cool. Now, cotton, being a very good absorber of water, helps in absorbing the sweat efficiently, and then, crucially, it exposes the absorbed sweat to the atmosphere over a large surface area for easy and rapid evaporation. This significantly enhances the natural cooling effect of sweating. Cotton helps evaporation work better.
So cotton helps the sweat evaporate faster, cooling us more effectively. Brilliant. Finally, here's a common sight. Why do we often see tiny water droplets forming on the outside surface of a glass filled with ice-cold water, especially on a humid day? Is this also evaporation at work, or is it actually something else, perhaps the reverse?
This is actually a related but reverse phenomenon called condensation, triggered by cooling, not evaporation.
Condensation, the opposite.
Yes. When you take some ice-cold water in a tumbler, the air immediately surrounding the cold glass gets cooled down significantly. The water vapor, which is a gas already present in that surrounding air, especially on a humid day, upon coming into contact with the cold surface of the glass, loses energy. The cold glass chills the air particles.
The gas particles lose energy.
Yes. When gas particles lose enough energy, they slow down, and the attractive forces become effective again. They get converted back into the liquid state, which we then see as those tiny water droplets forming on the outer surface of the tumbler. So it's the exact opposite of evaporation. Cooling causes gas to become liquid. Water vapor from the air turns into liquid water on the cold glass.
Wow. Condensation. So the water comes from the air, not through the glass.
Precisely, from the water vapor in the air.
Amazing. So from the refreshing feeling of a breeze on your skin after sweating to the simple comfort of cotton clothes in summer, what's constantly working around us, almost invisibly, thanks to the principles of evaporation.
Evaporation, you see, is constantly working to regulate temperature and keep things cool, an incredible natural process that influences so much of our daily comfort and the broader environment. It's a testament to the continuous, subtle activity of matter, always changing state, always transferring energy.
Mhm.
8. What you have learned, recap, and future thought.
Wow, that was a truly immersive deep dive into the fundamental nature of matter. Really comprehensive. We've covered so much, from the tiniest invisible particles that make up everything to the vast states of our universe, solid, liquid, gas, and the forces and energy changes that govern their transformation. Before we wrap up, could you help us summarize the absolute key, impactful takeaways from today's discussion for our listeners? Just the main points so they have a solid foundation to build upon.
Absolutely. Let's condense these powerful insights into what you have learned today. A quick recap. First, the fundamental truth. Everything around us, all matter, is made up of incredibly small, discrete particles.
Particles, check.
Second, matter in our surroundings primarily exists in 3 distinct states: solid, liquid, and gas.
3 states, check.
Third, the strength of the forces of attraction between these particles is highest in solids, intermediate in liquids, and lowest, almost negligible, you see in gases.
Force varies, check.
Fourth, conversely, the spaces between these constituent particles and their kinetic energy are minimum in solids, intermediate in liquids, and maximum in gases. Space and energy vary inversely to force, sort of.
Space and energy, check. And what about the arrangement of these particles in each state and the amazing ability of matter to shift between these states?
Right. Fifth, the arrangement of particles is most ordered and fixed in solids, giving them their rigidity. In liquids, layers of particles can slip and slide over each other, creating fluidity. While for gases, there's no fixed order. Particles just move about randomly and chaotically. Sixth, and vitally, the states of matter are not fixed. They are truly interconvertible.
They can change.
Yes, a substance can change its state by altering its temperature or its pressure. We also learned about direct changes. Sublimation is the direct change from a solid state to a gaseous state without passing through the liquid state. The reverse process, a direct change from gas to solid, is called deposition.
Sublimation and deposition, check. And that crucial distinction between boiling and evaporation and the factors that influence how fast something dries.
Indeed. 8th point. Boiling is a bulk phenomenon where particles from the entire liquid gain enough energy to change into vapor at its specific boiling point. Evaporation, on the other hand, is a surface phenomenon where only particles at the surface gain enough energy to escape as vapor at temperatures below the boiling point. Happens anytime.
Boiling versus evaporation, check.
9th, the rate of evaporation is influenced by several key factors: the surface area exposed, the ambient temperature, the humidity of the air, and the wind speed.
Factors affecting evaporation, check. And finally, that remarkable cooling effect we discussed, along with the concept of hidden energy, the latent heat that powers these transformations.
10th, and crucially, evaporation causes cooling because particles absorb energy, specifically the latent heat of vaporization, from their surroundings to facilitate their change of state. They steal heat.
Cooling effect, check.
And finally, we demystified latent heat of vaporization, the hidden energy required to change liquid to gas at its boiling point, and latent heat of fusion, the hidden energy to change solid to liquid at its melting point. These are energies absorbed not for temperature rise, but solely for changing the state, you see. And just to put some key quantities into perspective for reference, we measure temperature in Kelvin, mass in kilograms kg, volume in cubic meter, m, density in kilograms per cubic meter, kilom, and pressure in pascals.
Latent heat in units, perfect. That's a fantastic, truly comprehensive summary, tying all those intricate details together. And to leave our listeners with something truly provocative to ponder, something that builds on this incredible knowledge we've unpacked today.
Yes, absolutely. Consider this: how these fundamental principles of matter's behavior, the tiny particles, their incessant motion, their varying attractions, the energy involved in state changes, how these are not just academic concepts confined to textbooks or classrooms. They are, in fact, at the very heart of so many everyday phenomena we take for granted. Why your food cooks faster in a pressure cooker, how weather patterns form involving evaporation and condensation, the precise design of engineering materials based on their solid properties, and even how complex biological systems function within our own bodies, relying on diffusion and solutions. If we truly grasp the behavior of these tiny invisible particles, you see, we begin to understand and, in many ways, can even predict or manipulate the entire macroscopic world around us. So the thought to ponder is, what other everyday phenomena can you now explain using these characteristics of matter? Keep observing, keep questioning, and keep connecting the microscopic to the macroscopic. There's physics everywhere.
Fantastic. What an incredible journey through the very building blocks of our universe. Our sincere thanks to you, our listener, for joining us on this truly insightful deep dive into matter in our surroundings.
We truly hope this exploration has not only provided you with essential knowledge, but also ignited your curiosity, maybe, to look at the world with a fresh, more scientific perspective. These basic concepts are the very foundation for understanding far more complex scientific principles down the road, you see.
Absolutely. Keep those questions coming. Keep observing the wonders of matter all around you in the kitchen, outside, everywhere, and keep making those incredible connections. Until next time, stay curious and keep diving deep.